Hello and welcome back. In this video we'll continue looking at polynomial functions in section 3.2, and what we're doing is we're looking at the leading term of the polynomial. So the term with the largest power, and we're looking at the end behavior of the function. So what happens as the function goes farther and farther to the right or farther and farther to the left. So when n is odd, so when we have an odd power for a leading coefficient, and we have a positive coefficient for that leading term, our function is going to go in sort of both directions at the end. So far to the right we should be going up, far to the left we should be going down as we go to the left. If, on the other hand, our leading coefficient is negative, we end up flipping everything over. So far to the right, we'll end up going down, and then as we go further and further left, we're going up. If we have even n, because everything is even, we're going to be going in the same direction in both ways. So when an is positive, when we have a positive coefficient, everything is going up, and when we have a negative coefficient, everything is going down. So let's look at a couple of examples and just apply this. So, for instance, what is the end behavior of x to the fourth minus 4x squared? Well, we look at that leading term. So this is the leading term. The power is 4. So this is going to be even. And our coefficient here, which is hidden, is just going to be 1 times x to the fourth. This is going to be positive. So when we make this graph, maybe we don't know exactly what happens in the middle, but we know that since this is even, we're going to be going in the same direction to the far left and far right, and because it's positive, we're going to be pointing up. So who knows what's going on in between, but we know that it's going up in both directions. So this is essentially what the end behavior looks like. How about what is the end behavior of 2x to the third, x minus 1, x plus 5? Well, this doesn't quite look like a polynomial. I need to find the leading term. So let's simplify this. I'm going to leave the 2x to the third out here for the moment, and I'm going to FOIL these two binomials. So the first terms is x squared. The outer terms will be 5x. The inner terms, minus 1 times x. The last terms will be minus 5. If I simplify this, 5x minus x, well, that's going to be 4x. We still have that minus 5 at the end, and now I'll just distribute my 2x to the third. So 2x to the third times x squared, we'll have 2x to the fifth, plus this will be 8x to the fourth, minus 10x to the third. So again, our leading term, our most important term for determining what happens at the ends of the graph. So this is going to be our leading term. And now we have an odd power, but we still have a positive coefficient. And when our function has an odd power, we know that we're going to be pointing in different directions, to the right and to the left. And since this is positive, as x becomes more positive, the function will become more positive. And as x becomes more negative, the function will become more negative. Who knows what's happening in between? We know it's smooth and continuous, but as we go farther and farther to the right, we're going up. And as we come farther and farther to the left, we're going down. So let's see an application of this. So the function f of x is equal to negative 0.27 x to the third, 9.2 x squared minus 102.9x plus 400. This is a bizarre function, and it's kind of hard to see what's going on. But it says that this models the ratio of students to computers in the U.S. X years after 1980. So the question that's posed is, will this be appropriate many years after 1980? And while this seems like an odd question, if we think about what happens many years after 1980, well, that's when x is getting really big. So what this is asking is, as x becomes really big, what happens to our function, and does it seem appropriate? Well, when we look at the leading term of our function, it's negative 0.27 times x to the third. We have an odd power, and now we have a negative coefficient. So when we draw our function, as x gets really big, odd means that this will be pointing in different directions as we go to the left and right. Negative means that as x gets really big, this is going to be negative. So we're pointing down over here. So if we're pointing down, many years after 1980, we're going to be going further and further and further and further down. Eventually, if we go down far enough, we're going to be negative. So can you have a negative ratio of students to computers? That doesn't make any sense. Negative ratios, this doesn't make any sense, because we'll have a positive number of students and a positive number of computers. So there shouldn't be a negative ratio. A ratio of positive numbers is positive. So no, this won't make sense many years after 1980. This function is eventually going to be negative. And negative ratios of positive numbers, that doesn't quite make any sense. There shouldn't be negative 10 students to every computer. Can't even imagine what a negative student would be. So here we have, does the following graph adequately describe the end behavior of this function? We've got x cubed plus 13x squared plus 10x minus 4. So here's our graph, and it looks like the end behavior, it's going up as we go to the left and to the right. Well, we know how to find the end behavior, so let's look at this leading term. And again, we'll go, okay, we have an odd power, and our coefficient, which is just hiding, it's 1, is going to be positive. So we know that the end behavior of the function, since it's odd, it should be pointing in different directions, and since it's positive, as x gets really positive, the function is getting really positive, and as x is getting negative, that means that our function should be getting negative. So this function doesn't look like it describes this behavior. So the answer would be no. But this can be a little bit deceptive. If I were to do my best attempt to draw this function, what it looks like is the following. We still have this little dip here, but as we come further and further to the left, it actually just comes back down. So this is, in fact, going to be a good picture of what's going on, but only in a little itty-bitty box. So it doesn't really show what happens when x goes far to the left, as x gets really negative. It's just too close. We can't really see the bigger picture with this. So no, this doesn't adequately describe the end behavior. Even if this graph is correct, it just doesn't show enough. So the last thing that we'll look at in this video is going to be zeros of polynomial functions. And zeros are just a fancy term for the x-intercept. So, and there are lots of ways to describe this. These can be described as zeros. They're also called roots or solutions, specifically to this equation. So again, the x-intercepts are just going to be where our function crosses the x-axis. So knowing how many times it crosses the x-axis, where it crosses the x-axis, this would be useful if we tried to draw our function. So well, I'm showing my work here. I'll go through this step by step with you as well. So let's find all the zeros for this function. So again, a zero of a function is where the function is equal to 0. So all we're trying to do is solve this equation. And the technique that the book likes for these is for us to split up the equation into smaller parts that we can factor a little bit nicer. So I'm going to take the first two terms and I'll clump them together, and I'll take the second two terms and I'll clump them together, and again we're adding all of these. So in this first term I can factor out an x squared from both terms, so I'll be left with an x and a plus 2. And in this last term I can factor a negative 4 out of both of these. This is going to be negative 4 times x, and that's going to be negative 4 times positive 2. And then the trick here is, oh, we have the same term in both of these, so now I can factor out this. So if I factor an x plus 2 out of the first term, I'll be left with an x squared. If I factor an x plus 2 out of the second term, I'll be left with a minus 4. And we are getting closer and closer to being done. This first term, in fact, factors a little bit more. And this is one of the forms that's just nice to remember. X squared minus 2 squared, I can factor this into x plus 2 times x minus 2. And we still have that last term at the end. So if I'm going to multiply some numbers together to get 0, the only way I can do that is if one of those terms is equal to 0. So we have x plus 2 is equal to 0, or x minus 2 is equal to 0, or x plus 2 is equal to 0. Notice that we get the same equation twice because it shows up twice. So here, x could be negative 2, or x could be equal to 2 if I add 2 to both sides, or x could be equal to negative 2. So what are the zeros? These are going to be 2 and negative 2. So we see that here, negative 2 shows up twice. It shows up as a root twice to our equation. This is important, and it will help us understand what exactly happens at this root. So again, we'll just give this a name. If x is a 0 of a polynomial, and it's a 0 k times, we say that x has multiplicity k. So up here, we would see that 2 has multiplicity 1. If I can spell 1. Because it shows up once. Whereas negative 2 has multiplicity 2, because it shows up twice. The easy way to see this, we can look at all of the equations that pop up here. If I want to know where the roots of this polynomial are, well, I have to solve x is equal to 0 from there. I have to solve x minus 1 is equal to 0 from this guy. And I have to solve x plus 2 is equal to 0 from this guy. Well, so 0 is a root, 1 is a root, and negative 2 is a root. And if these are my roots, also known as zeros, what are the multiplicities? Well, 0 happens once, because this is just x to the first power. X minus 1 happens twice. And negative 2 is going to happen 5 times, because that's the power here. So the shape, which I'll briefly describe and then continue on in the next video, once we know the multiplicities, we know what happens to the graph at the root. If the multiplicity is odd versus even, different things happen. And the basic shape, if the multiplicity is odd, we're going to cross the x-axis. And if the multiplicity is even, we're going to come down, touch the x-axis, turn around, and go up. We're not going to cross. And I'll go through this more in the next video.